Welcome back to our astrophysics lesson series. Today, we're covering general relativity, a giant leap from gravity. In the early 1900s, Einstein asked why Newton's theory of gravity worked. He wanted to know why all masses attract each other. Einstein theorized that all masses distort the space-time continuum, which can explain the forces that masses exert on one another. The first thing that is important to understand is the idea of a space-time continuum. The space-time continuum is a 4D graph that we have superimposed over the universe. This is not a physical graph, just a model for explaining and measuring the universe. The variables of the continuum are mass, space, and time. This idea links the three dimensions of space to the passage of time. This graph makes it so that the reference frame of the observer does not impact the observation. If you look at a pencil from several different reference frames, it may appear to be several different lengths. If a period of time between two events is measured from several reference points, they may return different time periods. When the combination of space and time is used, however, the same results can be found regardless of the reference frame of the observer. We can use this trampoline as an example of the space-time continuum. Now, the real space-time continuum is 4 dimensions: length, width, height, and time. But for the purposes of this demonstration, we've collapsed down to just length and width. You can see that my little brother here is going to represent a larger mass, and this small basketball will represent a smaller mass. What we see is that he bends the surface of the trampoline, meaning he would warp the space-time continuum far more than this small basketball will. That's just because he has more mass. We can also see that if I let this ball roll, it will roll towards him because of its gravitational pull, because of the bending of the space-time continuum, and that it will accelerate as it gets closer to him because the gravitational force on the ball is increasing. Let's see. And as we expected, it accelerated as it got closer to my little brother. Which explains why Newton's law of gravity includes distance squared, represented by r squared, rather than r. If you look at a take from the trampoline experiment, we can see that when a smaller object is placed further from the large mass, it will accelerate at a certain rate. When it is placed closer to the larger mass, it will accelerate exponentially faster than it did at the further position. This shows how the distance between the objects has an inverse square relationship with the force of gravity due to the bending of spacetime. When an object is far enough away that the force is not too high, but is moving very quickly, it experiences what we call orbit. Orbit can occur at nearly any distance from the gravitational center, but the velocity and direction of movement must change accordingly. The hard thing about this topic is that it's difficult to visualize. The space-time continuum is not just one layer of trampoline. It's several layers that are stacked on top of each other and infinitely close together. So this means that a mass does not just warp the continuum on its bottom, but it warps the continuum all the way around the mass. We can use this planet and its moon as an example. If the moon approaches the planet from here, it will experience gravity. It will also experience gravity from here, 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 or here. That's because the continuum warps in all directions around both masses, not just on their bottom. This is the difference between real life and our trampoline example. So what this means is a meteor approaching Earth would experience gravity no matter which direction it's approaching from. If there was an empty universe with only a single mass, unaffected by gravity, that mass would warp the continuum around it. If this mass was set in motion, it would travel in a straight path along one of the lines of the continuum. When another object is introduced, we see that this object's trajectory would be bent towards the other mass. The object will then move forward in this new direction indefinitely unless acted on by another force. Geodesics is the study of these curved paths. This is the geometry that explains the shortest path along a curved surface. This idea is applied to relativity when we discuss the path that objects take when affected by the curvature of spacetime. Their path is along a curve because of the gravity of another object, so the geometry and math of the path they take is called geodesics. This video is in 2 parts. See part 2 on my channel.